Hi, this is the overview of the solution for part 2 of Lab 1. So let's start with the top-level module of the project. As you can see, the only two things that are instantiated in this top-level module for this part are the NEOS system and the SRAM controller module. So the ports from the NEOS system are exactly the same as part 1. Now for the SRAM controller, which is going to be an intermediate module between the NEOS system and the actual SRAM chip on the D2 board, you have your inputs, which are the Avalon bus inputs and the clock and reset. And then you have the outputs for the Avalon bus, which are the acknowledge and read data. Then you have all the SRAM chip signals, which are all outputs. Or, well, in the case of SRAM DQ, it's bidirectional. So SRAM DQ, then address, chip enable, write enable, output enable, upper byte, and lower byte. Okay, so just to go to the QSys setup just for a second, just showing you that it's exactly the same as part 1. Even the external bus bridge address space is exactly the same from 0 to 7FFFF. Alright, now moving on to the actual implementation of the controller. It's very simple if you wrote it the way I did, just assign statements and combinational logic. Now the acknowledge is the same as part 1 for the peripheral. It's just assigned to bus enable. The read data is going to depend on whether the bus enable is 1, and if it's a read, so that means read write is 1. So if what this statement is saying is if this condition is true, then read data will be assigned to SRAM DQ. Otherwise, it will be assigned to 16 bits of 0. The next line for SRAM DQ, when it is a write operation, SRAM DQ should be assigned to write data. And when it's a read operation or any other situation, you should have it set to high impedance or assigned to high impedance. So to say that it's a write would be when bus enable is on and when you have a 0 on RW. The SRAM address is just assigned to address bits 18 to 1 from the NEOS system, and this would, leaving out that 0 bit, converts the byte address into a half-word address, and the SRAM uses only 18 bits for its address, as you can see here. Okay, where were we? Yep, so chip enable is just set. So all of these signals here, all of these signals are active low. That's what the _n means. So the chip enable is set to the inverse of bus enable. The write enable is going to be activated when RW is a 0. Output enable should be a 0 when RW is a 1. So that's why we invert it. The upper byte is going to be the same as byte enable, except it's active low, so it's inverted, and same thing with lower byte. Inverted byte enable 0. Now, this implementation here is not completely safe. So if you wanted to put in extra redundancy to make sure that these other signals don't are deactivated whenever bus enable is not on, you should really put in bus enable into here. Like this. So in this case, you want bus enable to be true, and you actually want write enable to be false. so the read write is 0 for it to, but then you would invert it as well. So you want this section here to be 0 when it's a write. And you do something similar where you would incorporate bus enable into each of the other signals to make sure that it doesn't get activated when bus enable is not on. But this works too. So we'll just continue like this. Okay, so let's move on to test bench simulation. So I've got the SRAM test bench that I provided on Moodle here. Now this one is similar to the one from part 1, and using it is also quite similar. So just to go over what this does, it instantiates the SRAM controller and connects up all the inputs and outputs. It then reads in the generated file that I created. So in this case, we're using SRAM bytes and the short test. And then it sets the clock oscillation and also sets up the fscanf function that will read from the text file. Yep. So we'll skip ahead a bit, and now in this particular test bench we cannot test the read data validity, and that is because there is no device on the other end of the SRAM controller that acts as the SRAM chip. So I've commented out the section that checks the read data, and the rest should be pretty much the same, or well, not the same, similar to what was used for part 1. So we have an acknowledge check, which just checks against the expected acknowledge. Now we have the SRAM DQ instead of the write data, so it will check that when it's a read, SRAM DQ should be high impedance. If it's not, it will throw an error. When it's a write, it will check byte enable, and then according to what byte enable is, it will check the associated bits of SRAM DQ against the expected bits. And then it checks all the other signals according to the expected values from the text file down here. Okay, so running this is the same method used for part 1. So we set this as top level entity. We change the compilation to RTL simulation, and you had to have the 2 settings, so the tools and the assignment settings for model sim. So I've already done that, so we won't do that now. And then we can run the RTL simulation. So this should open up model sim once it's done. Okay, and once it's done, we can open up SRAM test bench. We can drag in all the signals that we want in our waveform. Open this up a bit. And then in the transcript window, we can type run-all. That will run till the end of the simulation. Okay, and then we can zoom full. Okay, so let's switch the radix to hexadecimal. Okay, so now if we zoom in a little bit, you will see that this will look similar to what you got for part 1, except now you've got the SRAM signals, which are slightly different on the other end of the SRAM controller. The only thing that you should really be looking at here, which is not going to be correct in terms of practical performance, is the read data. So this section here, where it is high impedance, is actually when the SRAM chip would have been returning the value that is being read out of the SRAM chip. So that's the only part that shouldn't be there. But yeah, we can't help that because there is no module to emulate the SRAM chip on the other end of the SRAM controller. So just ignore that section. That's blue for read data, but for the SRAM DQ, obviously it has to be high impedance at that point. So I did get one error here. Now it is expecting SRAM output enable to be a 1 at the very beginning. That's what that error is saying. So that is an issue that's come about because of the way I've implemented the SRAM output enable bits. So like I mentioned before, this signal doesn't take into account the bus enable. If it did, then at the very beginning it should be deactivated. Okay, so if you get that error, that is what that's about. Alright, we won't go through any more of the simulation because you should be pretty familiar with how to use that now. Okay, so what we will move on to now is actually running it on the D2 board. So first thing we need to do is switch over to full compilation and then set this as top level entity. So this will be compiling this part, and then we run the compilation. Okay, now that the compilation is over, we can program the D2 board. And then we can open up monitor program. Okay, so I've already got the project set up. All we need to do is compile and load this .s file that I have. Before we do that, so we'll just go through what it does. So first, it will load the boundary value, so the last address in the address space to the SRAM, and then it will also load a starting address into R2. So each of these loops is going to go through and do a store and load operation to every address within that whole address space. So the first one does store bytes and load bytes. The second one does store half words and load half words, and the last one does store words and load words. Now, you didn't need to go into this much detail for your solution. You didn't have to write to and read from every single address, but it helps to be thorough when you're testing. So if you didn't go through this process, then as long as you tested byte transfers to both odd and even addresses, half word transfers and word transfers, then you should be fine. Okay, let's go back here and compile and load. Okay. Okay, so so what I forgot to do was import the pin assignments, which I don't think I actually have on this computer. So I might just stop this and then continue when I've got it. Okay, so download the pin assignments. Let's import it first. And then we will need to compile again. So I will probably cut out the compilation part of the video. Okay, so now that that's done, let's go back to monitor program. We'll need to download the system again. And now compile and load. Okay, and now let's step through it. So after loading loading the boundary address and the starting address into R1 and R2, we go through and we start writing. So the first address that it's going to write to in memory. So if we query this, we're going to see that the SRAM will have a lot of random data initially. Okay, and that is because it starts up with random values, and since every address has a unique byte in the SRAM chip, you'll see that there's a lot of different values here, random values. Okay, so the first thing that this is going to write to is to address 0. So as I step over it, you won't be able to see it, but it's actually changed that to the value 0. So in my code, it writes the same address value into that address. So the next byte address should get the value 1. Yep. And then the next one will get 2 and 3 and so on and so forth. Okay. Now if I was to run through the whole thing and then pause it, you'll see that it went through. It's actually gone through and done the other half word and store word operations as well. So what we might do is just put a breakpoint at the end of the first loop, or at the start of this, I guess, and we'll run it through till that point, and then we'll go back and we'll check. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so forth. And now what we'll do is we'll step over to see it writing half words. So the first half word is all zeros. The second one should be the value 2, because it's increment the byte address by 2. And then 4, can't count this time. So the next one should be 6, 8, 10, which is A, and so on. So once again, what we can do is we can put a breakpoint at the start of the next section and run through to that point. And then if we check the memory, we should see that it's 0, 2, 4, 6, 8, A, C, E. Yep. So part of the code was also reading it back into one of the registers. So what we can do is when we're doing the store word loop, we can actually check that it stores, and now this is going to load it back into R3. Yep, 0. So the next one is going to store 4 and reads it back into R3, 4. Similarly in memory, see that the whole word is 0 and then the whole word is 4, and then the next whole word should be 8. And then we'll run it through and stop it. Yeah. Okay. Yeah, that was pretty much it for part 2.